So I want you guys to try the do now. Pause the video, play it once you're done. So it says the probability of winning a certain game is 0.5. It mentions a fixed number. It mentions the probability of winning. It also is binary because you can either win or you lose. So I'm thinking we're going to have to use our binomial distribution. So I'm going to check bins. So binary, we either win or we lose. There's only two options. That's good. It doesn't say each game is independent, but we can assume each game is independent of each other. You start a brand new game. So yes, it is independent. N stands for what? Fixed number. There are fixed numbers. It's either 10, 20, or 100, depending on what our choice is going to be. And then S stands for what? Same probability. So our probability, it says, is always the same. It's always at 0.5. So P is always equal to 0.5. So this does pass bins. So we're going to want to use our binomial distribution. So they give us three options. They give us the option of N equals 10. They say N equals 20. Or N equals 100, and you want to see what number we should use to maximize the probability of winning the prize. So, bear in mind, we have to win at least 70% of the game. So, 70% of 10 would be 7. So, we want to find the probability that X is greater than or equal to 7, because at least 70%. And for 20, it would be X is greater than or equal to 14. And for 100, it would be X is greater than or equal to 70. But our binomial CDF always starts at 0. So for the first one, we're starting at 7. So remember what we need to do, and this is like the trickiest part of the binomial CDF, is you have to be able to like interpret when we have to do 1 minus the complement. So for each of these, we're going to have to do 1 minus the probability. And what would be the complement of greater than or equal to 7? You could write it a couple different ways. The way I'm going to write it is X is less than or equal to 6. I guess you could also say less than 7 because there's no like 6.5. In this case, this would be X is less than or equal to 13. And probability that X is less than or equal to 69. So now we can just find each of these. So 1 minus the binomial CDF, 10 probability, and our highest successes we want. So make sure you label, that's the number of the fixed number of trials. P is the percent probability of success, and K is the amount of successes we want. And you want to do that for each of these. This one should come to 0.171875, and I'll fill in the rest real quick. And here's what you should get for each of the probabilities, and you should see by far the highest probability of winning a prize would be when you have 10 trials. So the correct answer would be A. You could also have not done any of that work for this one, and you could have just said, okay, I know the highest probability is going to be the one with the lowest amount of trials, so it has to be A also. Either of those, I did a lot of extra work, but if you reason it like that, A works also. So let's go to the next question. Take a second, read this question. So we have a bad flash drive, we have a good flash drive. So this is going to probably be binomial. So let's check the binomial distribution. So we either have a defective or bad flash drive. So we either have a bad flash drive or we have a good flash drive. So that's good so far. We got two options. Independent. Is this independent? Think about it. We have 10,000 flash drives. There is no replacement here. If we pick one of the flash drives, we're not replacing it with another one, so we're always out of 10,000. We're going to then be out of 9,999 after we choose one. So this is not independent. So can we keep on doing binomial distribution? Let's take a look. So what is the probability of picking a defective flash drive? So if 200 are defective, we have 10,000. So our first one would be 200 out of 10,000. That would be 0.02. So how about picking a second defective flash drive? So we're not putting that flash drive back in the mix. So we now have 199 defective flash drives, and we don't have 10,000 flash drives anymore. We have 9,999 flash drives. And when you divide that, we get 0.0199019902. And let's say we pick a third one. We have 198 out of now 9,998. That would be 0.019803968. What do you notice about these probabilities? They are changing, but they're not really changing by that much. So there is a rule when if you take a look at our sample is so our sample in this case is only 10 flash drives. Our sample is so much smaller than our actual our population, where we can still use the binomial distribution even if it's not independent, because the probabilities are changing by so little. We can still have a rough estimation it's going to be accurate. So that is exactly what the 10% condition is. So it kind of lets us bypass independence if we have a large enough population compared to our sample size. So when taking a simple random sample of size n with a population uppercase n, we can use a binomial distribution to model the count of successes so this lets us bypass the independence. And we're going to be using this, honestly, for the rest of the year. So as long as the sample population is less than 10% of the actual population, we can bypass independence and say that the probabilities are changing so little that we can still estimate it. Look how little these are changing each probability. So, let's look at the next question. Knowing what we know now, let's go back to the past example we had and see if that represents a binomial distribution. So we have to check our bins. So binary, it's either defective or bad or not defective, good. So there's only two options there. That's good. It's not independent, but we can bypass independence if our sample size is so much less than our actual population size. So that would be lowercase n. The sample size is less than 0.1 of uppercase n. So our flash drives here, random sample of 10 flash drives, is less than 0.1 of 10,000, because that is our population size. And 10 is less than 1,000. So that definitely checks out. So we can bypass independence. We're good to keep on going with our binomial check. Do we have a set number? Yes. And is 10. We're always picking 10. And our probability is roughly always the same because of the 10% condition. So it would be around 0.02 the whole time. So yes, we can use a binomial distribution because the sample size is less than 10% of the population. So I want you guys pause the video, play it once you're done. I want you to try this next question. So when you check bins, the I is the tricky part. Remember this we don't have a set number of all the U.S. teenagers. So what we would say for something generic like that is our sample size is 500. So that's where the 500 comes from. But all the U.S. teenagers between 14 and 18, we don't have that number. We know it's some ridiculously high number in the millions. So what you would just say here is 0.1 times all teenagers 14 through 18 in the USA. And there's definitely more than what had to be 5,000 teenagers in the USA, so that definitely checks out. Sample size is 500, and then it's always saying 12%. So yes, we can use a binomial distribution for this sample. And B, estimate the probability that 50 or fewer teens in the sample have debit cards. So let's first state what our variable is going to be. Does it say it up there? It does, so we actually don't need to say it again. So it's number of teens with a debit card. So we want the probability that X is 50 or fewer, so less than or equal to 50. And that's going to be binomial CDF, because we're counting from 0 to 50. We're not just counting 50, so it's not going to be PDF. 500 is our sample size. 0.012 is our probability. And we want to go all the way up to 50. Put that in the calculator. You should get 0.0932 as our answer. Let's go to the next page. So let's take a look at just a binomial distribution, the graph of 1. If n is equal to 10 and the probability of success is 80% or 0.8. So this is what the graph would look like. But let's say we want to up the number of trials. So let's up the number of trials to, say, 20. So you see how it changes a little bit. And then let's keep on upping those trials. Why not? The more trials we get, the better it's going to be. So let's keep on upping the trials to 50. Look at that. Oh my goodness, what happens to the shape of our binomial distribution as we increase from a sample size of 10 to 50? Or say we kept on going and going, what is it looking like? It's becoming more and more of, especially there, it's getting closer and closer to a normal distribution. So as the number of trials increases, the binomial distribution gets closer and closer to a normal distribution. So you better believe we're going to be using normal CDF to help approximate if our sample size is large enough. And how we tell if our sample size is large enough is called the large counts condition. So what the large counts condition states is that, you can read that, or it says the number of successes and the number of expected failures, so the number of expected successes and number of expected failures, are both at least 10, so they're greater than or equal to 10, then we can use the normal curve to approximate a binomial distribution. If both are not 10 or greater, we cannot use the normal curve to approximate a binomial distribution. So let's look at the next question. So given the previous example of the debit cards, would we be able to approximate our binomial distribution with a normal distribution? So we would have to check the large counts condition. So that would be the number of expected successes is greater than or equal to 10, and the number of expected failures is greater than or equal to 10. You'll also see people use Q for this. You can if you want to. I think 1 minus P is just easier because it's consistent with using P. But you don't have to. So the number of our sample size is 500, so that's lowercase n, times our probability of success, which is 0.12. It's greater than or equal to 10. And when you multiply that out, that is 60, which is greater than or equal to 10. Woo, that works. Okay. And then n, 1 minus P in this case. Oh, well, n is 500. And 1 minus P in this case is 0.88, is greater than or equal to 10. That's 440, which is definitely greater than or equal to 10. So yes, we can. It makes you explain your reasoning because the mean amount or expected amount, mean amount of successes and failures are both greater than 10. Greater than, or you can say greater than or equal to. So now we can use our normal distribution to approximate the binomial distribution. And to do that, we would want to do normal CDF. And 50 or fewer, so that means our lower bound is 0, or you can even make a negative 99999, not going to matter. Upper bound is 50. And then we need our mean, and we need our standard deviation. So we have to go back to the mean and standard deviation formulas for a binomial distribution. And remember, our mean is sample size times our probability of success. So in this case, our sample size was 500, and our probability of success was 0.12. So our mean is going to be 60. So I'll plug 60 in there. And our standard deviation would be our sample size times the probability of success times the probability of failure. So that would be 500 times 0.12 times 0.88, which is the square root of 52.8. So you can plug in square root of 52.8 if you want to. That makes it a little bit more exact. You can like round it a little bit, round it to like the 10,000th or something like that, and plug it in. So we should get, when you plug this in, something around 0.08438, and that would be our normal approximation. And when you look at, we just did this above for the binomial distribution, and we got something a little bit different. Let's compare them. So you could say, why would we do a normal distribution when it's a little bit less accurate than a binomial distribution? I had that same question for like the past 2 years. I was like, why would we do this at all? It's because we're not in AP Stats. We're not really working with very large numbers. One of my good friends is a doctorate in stats, and I asked him. I was like, I have no idea. Like I've asked this question so many times, and no one has the answer for me. And he said, just when you're working like the real world, when you have a binomial distribution, the numbers can get so large that a computer actually can't compute that in a timely fashion. So unless you have like a lot of money, if you're like one of the bigger businesses and you can compute the binomial distribution, and especially when the numbers get that large, the normal distribution is just so close to a binomial distribution where like the percentages will even be closer than this. So that's why we use a normal distribution. It saves time, it saves money, and some people just can't do that when it gets to such a large number because they don't have the technology for it. But yeah, that's it. The rest is classwork. Good luck. Feel free to send me an email if you have any questions.